Thank you very much. So I'm Axel Eriksson, and I will present our multi-mode platform. This work is done in Sweden in Simone Gasperinetti's group, and they were also interested in quantum enabling technologies and quantum thermodynamical experiments. And our effort on bosonic mode has the longer term goal here to move towards verifiable quantum computing or quantum speed up. So the fundamental question here is, if we as a field are able to produce quantum computers that can solve tasks that classical computers cannot, how can we put trust in the results of these computers if we cannot check the results directly? And then there are different proposals, and one proposal that we will follow here is from our collaborators in Paris. And the basic idea goes like this. We start with creating a bunch of bosonic modes and prepare non-classical states in them. Then we feed these modes into an interferometer, and then we do unbalanced heterodyne detection. And then it turns out that this will actually result in a hard sampling task. And then if we take our experiment and slightly tune this unbalanced heterodyne detection into a balanced version, then we can actually cast this hard sampling task into a simple task that we can solve classically, and we can use that as a verification task, such that we can verify that the hardware is doing what it should, and then we can experimentally do the easy work of slightly detuning it again, unbalancing the heterodyne detection, and then execute the hard sampling task. So this is the general goal. And the building blocks that we can use to achieve this could be, for example, to use snap plus displacement gates. And this is some experimental data from our group to do the single mode non-Gaussian state preparation. And to do heterodyne detection in stationary modes is actually quite difficult. But there we're working on a protocol which we call qubitine. And basically how this works is that you take your cavity and you swap out a small fraction of the state into a qubit. And then you measure sigma x or sigma y of this qubit, you reset it, you swap out a little bit again, measure, reset, and you do this quickly, like 100 times, and sum up the results. And then these actually constitute a single pull from a homodyne current. So for example, here we do this on a FOC2, and you can see the two dips corresponding to the FOC2, or here's a homodyne detection. And we have an efficiency of approximately 70%. And the nice thing here is that by changing an as trivial experimental detail as just in which order we do a sigma x and sigma y measurements, we can turn this from a balanced heterodyne detection to an unbalanced heterodyne detection. So thereby we can actually switch from this hard sampling task to the verification task. And in this talk, so we can do that switching. And in this talk, I will now focus more on the coupler here that we need in the middle. So the platform that we want to create is a all-to-all connected four-mode platform with some coupler in the middle. Again, the major goal here is to go towards verifiable quantum speed-up. But we're also quite interested in multi-mode non-Gaussian operations. So for example, tri-body interactions. And some of the wanted ingredients then are linear beam splitting for the interferometer, and then also controllable tri-mode squeezing. So one option could be to put in a snail-based coupler, and we showed that if you tune this into the curve-free point, it approximately gets into a linear system if you don't drive it, and if you start to drive it, you can actually engage nonlinearities and, for example, do this tri-squeezing in the single mode. So this could be an interesting candidate, and it has already been used, this snail coupler, to do Beamsplitter in bosonic modes. And it works very well. One downside with it is that if you have multiple modes like this, in the general case, the cross curve between these modes will actually not cancel at the same flux point, because it depends on the different frequencies that are involved. So if you have multiple bosonic modes at different frequencies, generally they don't cancel at the same time. So we will actually put in, and then another very, very nice suggestion is to use a link that becomes super linear and clean if you don't drive it. And if you drive it, you can then drive beam splitting. So it's a super clean, nice linear beam splitter coupler. But the downside with this one for us is that it cannot do, for example, these tri-body interactions. It doesn't have that kind of operation. So what we will put into our coupler is an ATS. And we will bias this such that we cancel out all the odd static nonlinearities and the fourth order static nonlinearity, which helps us to create a quite linear beam splitter, which was one of the ingredients we need. But we still have a quite sizable three-body interaction such that we, for example, could do controllable tri-mode squeezing. And if we look on the flux map, this is where we would actually be wanting to sit with our flux bias. So we have a distribution of the frequencies involved in this chip, and we can then see how the coupler frequency tunes as a function of the two different fluxes in the arms. And we can identify the plus and the differential flux directions. And we can also see that this red dot is approximately where we would like to be sitting to cancel these nonlinearities. So if we move over to characterizing the nonlinearities, we can start with the coupler self-curve, and we can see that if we sweep the flux, we can cross zero here at this point. And then if we move over to cross-curve between the cavities, we can also see that, for example, the cross-curve between cavity 1 and 2 also cancels out in the neighborhood of where the self-curve cancels. And then if we move over to beam splitting, we can start to drive the system. We drive at the difference frequency of the two modes. And we can see that if we prepare a FOC1 in one of the cavities, we can swap it back and forth between the two cavities. And we can also study how the beam splitting rate changes as we move along the flux map. And for example, here we beam split a couple of different combinations of the branches, and we can see how the beam splitting rate changes. And generally here you can see that this is actually very slow beam splitting, and we now have next generation devices in the fridge where the beam splitting rate is considerably higher. Okay. So to summarize, we have or are building this multi-mode bosonic platform where we have 4 cavities, all told connected via this ATS-based coupler. And we have studied, for example, here the nonlinearities, so the cross curve of the cavity, and we can cancel it out at this flux point. We can also see that we're able to beam split multiple modes in this platform. And again, the beam splitting rates and the coupling rates in general are very small, and we want to boost them, and we have new devices with higher rates. And we also have a prediction or an estimate for how large the tri-mode squeezing rate would be. So here it could be around 10 kilohertz, which again is also something that we would like to boost even higher. But then now when we're starting to build this platform, we can start to do quite a lot of interesting things. So for example, we could take pairwise 2 and 2 modes and beam split them simultaneously with this copper. We could also maybe produce non-Gaussian states in the copper itself and swap that out to the different cavities. And we could also use this tri-body interaction to do 3-mode non-Gaussian operations like tri-squeezing, for example. And then we're also working towards verifiable quantum speed up, as I mentioned in the beginning. Thank you.
Thank you. Yep, go ahead.
Thanks for the good talk. You mentioned that you took not to use scale because the curves for all the modes don't cancel out at the same conditions. Did you test that as well for the ATS? Can you cancel them all out?
That is exactly what we want to show. So this is only showing 2 branches. There can be different reasons, and this is definitely what we want to do next to show that we are able to do this. Some reasons for why they might not cancel at the same time is that if you have some asymmetry between the two outer junctions, then you need to bias yourself slightly to the side instead to do this cancellation. So it should still be possible, but it will not be along the very diagonal. But basically what you need to first the second approximation there is that if you can cancel the 4th order and the 3rd order static nonlinearities at the same time, you basically are not sensitive to these differences in the frequencies anymore. So that's basically the idea. So if you're able to cancel these at the same time, of course, then there's always higher order corrections, but then you will actually do a quite good job at canceling these.
Is there any other questions from the audience?
Maybe I missed it. Did you say how many, like, is the near inductance in your ATS near inductance
It is the three junctions we use here. So that is how we actually can still have a quite sizable third order driven interaction. So if we would have like an array here, we would not have that. Like if you would really turn this into a link, for example. Then you don't have the third order drive activated on your thing. How large the cross query is? So if we look here, we're basically able to, also what you see here, I mean, the cross query is super small, again, because this device has very, very weak interactions, and we want to boost that. So in the newest device, it's like more than a factor of 10, 10 times stronger. So this is the order of the cross query that we are able to achieve in this weakly coupled device. So it's a couple of hertz. Yeah, exactly. That's what we aim to do.